Hello. Welcome to the Royal Society for the premier biological lecture of the year, the Croonian Lecture. I have a few things to say which are called housekeeping before we start. I'm supposed to introduce myself. I'm John Scahill. I'm the biological secretary of the Society. And please make sure your telephones are switched off. There are no planned fire evacuations tonight, so out through that door or the way you came in, if the bell rings. There are questionnaires on your seats, I think, and I'm supposed to encourage you to fill these in because they're supposed to be very valuable in the planning of these things. And now I've simply got, the thing is being webcast and recorded. I don't think that matters to you. It matters to us because we're not supposed to move very far away from this thing here. So the Croonian Lecture is an annual event. It was begun as a series in 1738. It's named for William Croon, who was one of the original fellows of the Society. And when he died in 1684, the plans for the lecture were found in his papers. Tonight, this lecture celebrates the work of Professor Nick Davies, who's professor of zoology in the zoology department in Cambridge. And his work, as you probably all have read, is on the co-evolved responses of brood parasitic cuckoos and their hosts, the process of co-evolution and adaptation, and the extraordinary biology of these unusual birds. About a couple of weeks ago, we had a trailer of his work on the BBC at 9 o'clock in the morning, which I was fortunate enough to hear. And of course, earlier this year, his book, Cuckoo Cheating by Nature, was published. So with introductions like that, it's just about unique, and it's my great pleasure to welcome Nick Davies to give his talk.
Well, it's a fantastic honour to give this lecture. Thank you, John, very much for your kind introduction, and thank you to Katrina Ross for organising this evening so well. And most of all, thank you all for coming. Well, science can start in many different ways, and I'm a bird watcher, so I often begin with a bird. And I think my job this evening is to try and persuade you that despite the weather, this is a very nice evening to go bird watching. And this evening's star is the common cuckoo and its extraordinary natural history. It raises, I think, some very interesting questions about evolutionary arms races. Now, the familiar two-note call of the cuckoo is our harbinger of spring. Summer is a-coming in, loud sing cuckoo, says the oldest English song. The call set the time for spring ploughing in ancient Greece. Indeed, we've probably been listening out for cuckoos ever since our ancestors walked out of Africa tens of thousands of years ago. But for many small birds, the cuckoo's arrival heralds potential disaster. Here, it's the commentary of Ted Hughes, the poet, that first ribald whoop as a stolen kiss sets the diary trembling. But it's the haunting chuckle of the female that announces the deed is done. So first of all, you'll hear the male's call, a rather better version than mine, and then the ominous female chuckle. The female utters that chuckle after she's laid each egg. It sounds like a call of triumph at a trick complete. for she's not only our harbinger of spring, she's nature's most notorious cheat. Aristotle knew this over 2,000 years ago. It lays its eggs in the nest of smaller birds. They do not bring up their young. And here's the cuckoo, having removed a host egg, laying her own in its place, and then she's off. She'll never even look back at what she's done, and there's her egg. She'll never see her chick either. Many females are already halfway back to Africa before their chicks have hatched out. And yet for the hosts, the worst is still to come. They're now sitting on a bomb set to explode in 11 days' time, one which will destroy their clutch. Aristotle knew this too. When the young bird is born, it casts out of the nest with whom it has so far lived. But his statement seems to have been forgotten for over 2,000 years ago, and the credit for the first detailed description goes to Edgar Chance, the father of vaccination. And in 1788, he published a paper in the Philosophical Transactions of the Royal Society, whose full title then was Philosophical Transactions, giving some account of the present undertakings, studies and labours of the ingenious in many considerable parts of the world. In the 1788 volume, there were papers by Erasmus Darwin, Charles's grandfather, on why it gets colder as you climb mountains. One by William Herschel on the newly discovered planet Uranus. And alongside we have Edgar Chance's down-to-earth paper, modestly entitled Observations on the Natural History of the Cuckoo. And it begins, "Dear Sir, having at your request employed some of my leisure hours in attending to the natural history of the cuckoo, I beg leave to lay before you the results of my observations." And after such a courteous beginning, what comes next is a shock. "To my astonishment," wrote Jenna, "I saw the young cuckoo so newly hatched in the act of turning out the host young. The mode of accomplishing this was very curious. The little animal, with the assistance of its rump and wings, contrived to get the bird upon its back, and making a lodgment for the bird by elevating its elbows, clambered backwards with it up to the side of the nest till it reached the top, where, resting for a moment, it threw off its load with a jerk. I afterwards put in an egg, and this by a similar process was conveyed to the edge of the nest and thrown out. And Jenna pointed out that the young cuckoo's got a broad back with a hollow, nicely designed for securing the lodgement of any eggs and chicks that it tosses overboard." Well, Jenna's account was met with widespread disbelief, and it's not surprising because even when you see it yourself, you can hardly believe your eyes. If that wasn't sufficiently extraordinary, the whole thing often takes place while the female reed warbler is sitting on the nest. Here, from below her, the young cuckoo has burst up and has pushed her off. And just keep an eye on her and the egg, because the next thing that happens is this. She watches as one by one her eggs and any chicks get tossed out of sight, and yet she does nothing to interfere. And so the cuckoo takes command of the nest, and here it is, just about to fledge 17 days later, now 7 times the weight of the little warblers that tend it, just as if it was a chick of their own. Now, to early naturalists, this made absolutely no sense at all. John Ray regarded animal design as a reflection of the wisdom of God, and he thought the cuckoo's lack of care for its young was just absurd. Gilbert White, in the Natural History of Selborne, went further and said it was a monstrous outrage on maternal affection. It's almost as if they were saying to the cuckoo, if you don't love your offspring, why do you bother having them? And they suggested, therefore, that the cuckoo was abnormal, that the creator had simply done a bad job. French biologist Harrison wondered if the cuckoo's stomach was perhaps too large to permit it to incubate its eggs. And Gilbert White dissected a cuckoo, but the gut seemed normal, so that didn't seem to be the answer. Edgar Chance thought maybe it's got abnormal behaviour. Perhaps that early migration just leaves no time for parental care. And what on earth were the hosts doing? Well, it was assumed they were only too pleased to give the poor cuckoo a helping hand. And here's a typical quote: "What delight birds show when they see a female cuckoo approach their abode. They give thanks for the honour which the great bird confers upon them by selecting their nest for its own use." Well, these quaint views were summarily dismissed by Charles Darwin. And in The Origin of Species, in the chapter 8, which was all about instinct, about how behaviour can evolve by natural selection, his prime example was the natural instincts of the cuckoo. And his first point was that parasitism is not defective, it's positively advantageous. Freed from the burden of care, the cuckoo can lay more eggs than any parental species. And in fact, we now know parasitic cuckoos are especially prolific. And so Darwin said parasitism should actually be favoured by natural selection. It should evolve from parental ancestry. Well, we now have a family tree for the 141 species of cuckoos in the world, and only 59 of them, that's just over 40%, are parasites. The rest are parental species, just like the birds in your back garden. They build their own nests and look after their own eggs and chicks. It's a very ancient family, dating back to some 60 million years ago, but it's very clear that parasitism has evolved 3 times independently in this family tree within the cuckoo family. And parasitism is the later branches, so it has indeed evolved from parental ancestry, just as Darwin suggested. And in fact, the 3 independent groups of cuckoos have different chick behaviour. So our cuckoo is part of this clade here, where the cuckoo chicks eject the host eggs from the nest. The crested cuckoos behave differently. They're raised alongside the host chicks, but they're very selfish in their begging, and often the host chicks starve to death. And the New World cuckoos in South America have got little hooks on the tips of their beak with which they slash the host chicks to death. There are some other brood parasites. There are cowbirds in North America. There are some African finches as parasites, and there are some honeyguides in Africa too. And there's one wonderful cuckoo duck, which here has laid its egg in a gull's nest, and here's the little duckling just hatched out alongside a gull chick. And if you add up that total, and I've got my numbers right, that's 102 cuckoo-like species in the world out of 10,000 bird species. That's 1%. Well, if, as Darwin suggested, parasitism is so advantageous, why just these few? There seems to be an unexploited workforce out there for other potential parasites. Well, maybe life as a parasite's not so rosy after all. First of all, the adults got to find host nests, and then the chicks have got to be tuned into raising by a foster species. Why, for example, doesn't this duck grow up thinking it's a gull? But there's another factor which might limit parasite success, and this was Darwin's final point. And that is, hosts don't accept cuckoos and other parasites through benevolence. They get tricked, or they follow what Darwin called a mistaken instinct. Darwin likened the natural world to an entangle bank, and he said there's a constant struggle throughout nature between the instincts of one to escape its enemy and the other to secure its prey. So the idea is that even if the physical world remained constant forevermore, evolution would still continue relentlessly as predators, parasites, and competitors did battle to try and outwit each other. So in theory, there should be an arms race between the host and the cuckoo. Hosts should evolve defences, for example, chucking out cuckoo eggs to save the rest of their brood. And then cuckoos should reply with trickery, and that should then lead to better defences, better trickery, and so on, a kind of ding-dong battle between the two parties. And this is why I became fascinated by cuckoos. They provide, in effect, a window onto Darwin's entangle bank, and one that we might unentangle by simple experiments. And yet the sight of a little pipit feeding an enormous cuckoo chick makes you wonder why they're apparently being so incredibly stupid. Do hosts really have any defences at all? Well, to see this, we need to go right back to the beginning to see how the cuckoo lays her egg. And the credit for this goes to Edgar Chance about 100 years ago. And here he is in his tweed suit and tie. Birdwatchers used to look very smart in the old days, getting into a little twiggy hide on a common in Worcestershire to film the laying for the first time. And one of his discoveries is that this laying visit takes less than 10 seconds. So no wonder no one had witnessed it before. And to make sure that Chance was waiting in the right spot, he often destroyed all the other available nests nearby. And this is what he saw, narrated by David Attenborough.
Oliver Pike is one of the earliest wildlife films ever made. Once Chance had decided which pipit nest the cuckoo was going to target, he placed his hive and camera close by, hoping to solve the mystery of how the cuckoo deposits its egg. This is what he found. The female cuckoo glides in from a distant tree to a pipit nest she has been observing carefully for several days, concealed in a tuft of heather. Next, the cuckoo hops on the ground and lays its egg directly into the nest while the adult pipits try to attack her. A very determined Edwardian naturalist had finally solved the age-old riddle. The cuckoo lays directly into the herd.
Now, Edgar Chance is one of my all-time heroes. His observations are absolutely brilliant. And this is a summary of the sequence that he discovered. This cuckoo is actually laying in a reed warbler nest, which is the main host we've watched in the fens. Now, female cuckoos, we start in the top right here, are defend territories containing some 20 to 40 host pairs. And I thought I was a good bird watcher until I started watching cuckoos, and they are absolutely in a different league. Female cuckoos are very secretive. They monitor the progress of the host nests, and then she times the laying of each of her eggs, just one per host nest, to coincide with the laying period of the host. And she's also a manipulator too, because if a nest has got a completed clutch with incubation already underway, the female cuckoo will swallow the whole lot, and the hosts then are forced to build a replacement nest which the cuckoo can parasitize. So by farming clutches in this way, she makes available nests throughout the season. Having chosen a suitable victim for her day's egg, she glides down, picks out one of the host's eggs, lays her own in its place, and she's off, uttering that chuckle all within 10 seconds. And you can't believe she laid in that short time, but there's the cuckoo egg lying alongside the two remaining host eggs, and the match to the reed warbler's own eggs is really rather wonderful. Now, has this cuckoo sequence evolved to trick the hosts? And that was the starting point for our study something like 30 years ago on Wicken Fen. And Mike Brooke and I monitored reed warbler nests, and we found that between 5 and 10% of them were parasitized by cuckoos. But the hosts don't get fooled every time. 20% of those cuckoo eggs got thrown out. The reed warblers spotted the deception, punctured the egg, and tossed it overboard. Now, what cues are the reed warblers using to spot the cuckoo egg? Well, we decided that the best way to test this was to become cuckoos ourselves and make model eggs and paint them various colours and have fun going round popping them into host nests to see whether they got accepted or rejected. And our nest searching once led to us being reported to the local police. And here, Mike Brooke is explaining to the policeman that he's actually not collecting eggs, but rather he's putting extra eggs into birds' nests. And rather surprisingly, or not surprisingly, the policeman's finding this very difficult to believe. Well, the first question we asked is, why has the cuckoo evolved egg mimicry, a beautiful match to the host eggs? Well, Darwin said this is to deceive the hosts who would otherwise notice an odd egg in their nest. But interestingly, Alfred Russel Wallace had a different idea. He was very impressed with how well camouflaged birds' eggs are. And if he thought that the hosts had to have their eggs camouflaged, then perhaps the cuckoo should have a camouflaged egg too, so that the two parties had independently evolved cryptic eggs to beat predators. Well, we could test between these two hypotheses with our model eggs. And what we found was that 70% of our models which differed from the reed warbler's eggs in colour got thrown out. But if we painted our models to match the reed warbler's eggs, only 3% got rejected. No differences in predation between those two treatments, so Darwin was right and Wallace, in this particular case, was incorrect. Now, it turns out that the reed warblers aren't simply adopting the rule, chuck the odd one out, because if you give them 3 foreign eggs, so that their own eggs are now in a minority, they'll still throw the foreign eggs out. And other experiments have shown that what the hosts do is that they learn what their own eggs look like the very first time they breed. And these are some nice experiments done by Arnon Lottem. So these are the responses to a foreign egg of an old female who's bred before. The rejection doesn't take place till she's finished her clutch. Well, if you replace her last laid egg with a foreign egg, she rejects it. If you replace her first laid egg with a foreign egg, she rejects that too. If you replace each of her eggs soon after laying with a foreign egg, so she ends up with 4 foreign eggs, she'll reject them, all of them. And the way she does so is very interesting. What she does is she rejects them one by one, and then when she sees that her nest is empty, she deserts. So she's just built to make one decision at a time. Well, now if you do the same experiments with young females breeding for the very first time, you get a different result. If you replace their last laid egg with a foreign egg, they reject it. So they seem to have learnt from early on what their own eggs look like. But if you replace their first egg with a foreign egg, they accept it. They've misimprinted on this foreign egg and included it as part of their own set. If you replace all their eggs, they'll accept them all too. So it looks as if young females learn the very first time they breed what their own eggs look like, and in this particular experiment, we've tricked them into learning a foreign egg as part of their own set. And that might explain why not all our foreign eggs get rejected. If you remember, it was only 70%. And that's roughly the proportion of first-time breeders on the fen. So it could be that they too were tricked into accepting one of our model eggs as their own through learning. Now, cuckoos don't only evolve a very good matching egg, their egg size is tiny for a bird as big as the cuckoo. This is the size of egg that you'd expect a cuckoo to lay, and indeed this is typical of non-parasitic cuckoos. And when we put these giant eggs into host nests, many more of them were rejected by the reed warblers than small ones. So the cuckoo's eggs got to match in size pretty well and also in colour too. Why does the cuckoo remove a host egg? Well, at first we thought this was because the hosts count and would notice an extra egg in their nest. But surprisingly, that's not the answer, because the hosts will accept our model eggs even when we add them to the clutch. So there must be another reason. Perhaps cuckoos are looking out for prior cuckoo eggs, which would hatch first and eject their own egg. Well, that doesn't seem to be the answer too, and that's surprising, because cuckoos just remove an egg at random. They don't select other cuckoos' eggs for removal. They should do, but they don't. Instead, it seems that the main reason for removing an egg is that it improves incubation of the clutch, it makes sure there aren't too many eggs in the nest, and the female gets a free meal while she's on the job. She swallows the egg that she removes. And that raises the question, why doesn't she remove all the host eggs? Well, again, our experiments provide the answer, and that is that hosts will always desert a single egg, but never a single chick. And that explains very neatly why it's the cuckoo chick which has to do the ejection, not the mother cuckoo earlier on during laying. And finally, what about that speed of laying, that incredible 10 seconds discovered by Edgar Chance? Is that important too? Well, we tested that using a stuffed cuckoo, which we placed on a reed warbler's nest. And you can see this poor cuckoo had a rough time. The reed warblers pile in and they mob it and sometimes pull feathers out. But the interesting result is that having been alerted by a cuckoo at their nest, they're then much more likely to reject an odd egg. So it's very important for the cuckoo to be fast to avoid alerting the hosts. Well, the outcome of all these host defences, which we discovered in other species apart from reed warblers, is that the cuckoo has evolved into distinct host races. The race that we watch in the fens specialises on reed warblers and lays a green egg to match. If you go to the moors of western and northern Britain, there's a different race, a genetically different race of cuckoo, genetically programmed to lay a brown egg, which matches their host, the meadowpipit. On the continent of Europe, there's a race of cuckoos which parasitises great reed warblers, and that's got a rather nice spotted egg, which looks just like the great reed warbler egg. And our experiments show that all these hosts are fussy, so it's not surprising that their cuckoo race has evolved a good matching egg. The exception that proves the rule is the host race of cuckoo that targets dunnocks or hedge sparrows. There's no match at all, at least to our eyes, and our experiments show why. It turns out that dunnocks will accept any coloured egg in their nest. In fact, they'll even accept a whole clutch of model eggs different from their own. So that shows that the cuckoo race will only evolve egg mimicry when its particular host is discriminating. Now, back in the old days, we used to gauge the match between a cuckoo egg and a host egg using human vision. And that simply won't do, because birds have got different visual systems to our own. We've got 3 colour cones, but birds have got 4. So this is the wavelength to which these 4 cones are attuned. There's one tuned to red, one to green, one to blue, and birds have got an extra cone tuned to ultraviolet, bluer than blue, if you like. And if you now compare the match between the cuckoo egg and the host egg, and this is just one example, across all the wavelengths visible to birds from UV right through to red, the match is fantastic right across all those wavelengths. Now, what we really want to know is how would a bird's eye see these different colours? And this is a puzzle which has been cracked by Cassie Stoddard and Martin Stevens. And they use this really rather nice tetrahedron to vision what's going on. So the 4 apexes of this tetrahedron represent the 4 colour cones, ultraviolet, blue, green and red. And then what you can do is you can take the colours on a host egg and you can map where they are in this space in the sense of how the 4 colour cones will be stimulated relatively by each colour. So here we've mapped this colour on this spot, and here we've mapped the background colour too. And you end up with a cloud of points which represent how a bird will see its own eggs. And now you do exactly the same for the cuckoo's egg, so you have a cloud of cuckoo points, and you simply see how well the 2 clouds match up. And that's what's plotted in this graph here. Here we're plotting how well the 2 clouds match up against how fussy the hosts are at rejecting eggs unlike their own. From the dunnocks over here, who show no fussiness not whatsoever, and there's no mimicry, here, right through to bramblings, which are incredibly fussy, and there the cuckoo match is absolutely beautiful. And in fact, there's a nice positive correlation there, showing that the fussier the hosts are, the better the cuckoo egg mimicry. Now, you might think cuckoos can't do blue, but they can, because there's a race which parasitizes redstarts in Finland, which has evolved a beautiful matching blue egg for fussy redstart hosts. The reason it hasn't done blue for dunnocks is simply the dunnocks don't discriminate. So let's go back to the scheme which we suggested at the start. We've now got good evidence for this top arrow here. Cuckoo egg trickery in the form of egg mimicry only evolves in response to host defences. And now we want to ask, does this arrow back the other way work too? In other words, if host defences evolve specifically in response to cuckoo parasitism. Now, wouldn't it be great to go back in time and test redstarts before they were parasitised, and the prediction would be that they would accept odd eggs and we'd have a situation like this on the left. Well, behaviour doesn't fossilise, so we can't go back in time, but we can do an equivalent experiment. And the equivalent experiment is to pop model eggs into the nests of species which are unsuitable as hosts, which you can be pretty sure have never had an arms race with cuckoos, either because their diet's no good for raising baby cuckoos, namely a seed diet, or because they nest in little holes to which the female cuckoo can get no access. And when you pop model eggs into the nests of these species, you find they don't reject eggs. So it looks as if the starting point in the arms race is really for no host defence. Now, the egg arms race doesn't end there. It's not just simply hosts evolving fussiness about odd eggs. And naturalists aren't the only ones to wonder about the natural world. At about the time that Darwin was finding finches on the Galapagos, John Clare was finding poems in the English countryside. And one of his most lovely poems is about the yellowhammer's nest, which the yellowhammer is called the scribble lark because of these wonderful scribbles on its eggs. And John Clare wrote, 5 eggs, pen scribbled o'er with ink their shells, resembling writing scrawls which fancy reads as nature's poesy and pastoral spells. Well, 80 years later, a naturalist working in Africa suggested that this wasn't just poetic whimsy, but there really was some signature going on with these markings. And this naturalist was Charles Swinton, working in Africa in 1718, and he wrote the following: "I doubt whether mimicry by the cuckoo would end the matter, for when a cuckoo's egg became indistinguishable, in other words, a perfect match, variation in the host's eggs would still afford means of distinguishing them from the cuckoo's, and a race might have taken place between the host and the cuckoo's eggs." So this brilliant suggestion by Swinton is that these spots on host eggs are the way the host is signing its own eggs with spots and squiggle, in effect writing, "This is my egg." And the cuckoo then has to match by evolving a forgery with the same dots and squiggles, writing, "And so is this egg." And we can imagine an arms race of never-ending signatures with the forgeries by cuckoos trying to keep up. Now we of course use signatures to sign our own possessions, and here are 3 famous naturalist signatures on the top here. But if there are forgers at large, should we go in for something more elaborate, as Queen Elizabeth I did, or would even a simple signature like that of my little grandson do just as well? Well, the ideal signature should have 3 features. First of all, it should be replicable, low variation within a clutch. And what that means is the female should write her squiggles and spots exactly the same on each of her eggs, as she's done here. Then they should be individually distinct, so there should be differences between females of a species, which they are here. This female signs her egg in a very different way from this one. And then they should be difficult to forge. And you might wonder, well, does that mean you should make it as complicated as possible? Well, a recent study by Cassie Stoddard, Rebecca Kilner and Chris Town has examined this using a computer program which they call Nature Pattern Match. And what the computer does is it looks at the spots and squiggles on an egg and recognises patterns in rather the same way that our brains do, namely by detecting key features, the shape and the size and the contrast and the orientation of each marking. Just as a mapper might be looking for hills and valleys in a landscape. And then what it does is it compares eggs by scoring the number of matches. So these 2 eggs were taken from the same clutch, and there are lots and lots of matches. These 2 eggs were taken from different clutches, and there are fewer matches. In fact, in this example, there is one match just by chance, this one here and this one here, even though they come from different clutches. And then what the computer did is it gave each host species a score of how easy it was to assign an egg to the right clutch. So here, a computer was given this egg and asked, which of all these clutches does it come from? And bingo, it got it right. It assigned them to this clutch here. And then this was done for different host species to give a recognizability score to each host signatures. And the results are shown here. So along the bottom here, we're scoring the accuracy of the mimicry by the cuckoo, how well the cuckoo's egg matches the host's eggs, how well those clouds of colours match and how well the spottings match, if you like. From very good in the brambling to absolutely hopeless in the dunnock. And here we're giving a recognizability score to the host signatures, how well a particular egg can be assigned to its right clutch. And you can see that as cuckoos get better at tracking hosts' eggs through mimicry, hosts evolve better signatures. So there really does seem to be an arms race, just as Swinton had suggested. What's very interesting here is it's not more spots the better. Actually, the brambling has got a more distinctive signature than the great reed warbler, even though there are fewer spots. And it seems that the spacing between the spots matters as well, providing distinctive landmarks that stand out better against a background. When you fly over the Lake District, it's always easy to pick out the Langdale pikes because of those distinct peaks, but also their spacing from the rest of the mountains in the landscape. Where you get lots of complicated mountains, it's sometimes difficult to know where you are. So in a forgery race, maybe little Leo would do even better than Queen Elizabeth I. Well, the prize for the very best signatures go to a remarkable bird in Africa, studied by Clare Spottiswoode. So we're just going to do a little trip out now to Zambia. And here there is a cuckoo finch with cuckoo-like habits at work, and it parasitized a little African warbler called the tawny flank prinia. And here's Clare enjoying fieldwork with two of the biggest smiles in Africa. Her local nest finders are absolutely stunningly good at finding even cryptic nests. And this is why the prize should go to the tawny flank prinia. These are 8 different females, all nesting in the same field. A female always lays exactly the same egg type, but the differences between females are absolutely stunning. They differ in background colour, they differ in marks, and they differ in the dispersion of the marks. So this one has big spots, this one has small spots, this has squiggles too, but all the squiggles are at the blunt end. Here they're spread out amongst the shell. Well, Clare wondered if these signatures enabled a female to recognise her own eggs. So what she did is she gave females an egg of another female as a test. And females were very quick to reject an egg that differed from their own. And they integrated information from all those 3 features. So a big difference in one feature led to rejection, but a small difference in all 3 features also led to rejection too. So to succeed, that cuckoo finch is going to need fantastic forgeries. And indeed it has. Round the edge here we have the array of signatures by the host, the little tawny flank prinia, and here are the range of forgeries by the cuckoo finch. Now what each cuckoo finch should do, of course, is know her own egg and target only those prinias for whom her egg is a good match. So if you're a cuckoo finch laying this type of egg, you should target prinias with this signature, because it's the only one that you're going to get away with. Well, Clare found actually that these cuckoo finches are not so clever. They lay haphazardly and suffer lots of rejection. So signature diversity within a host species is in fact a wonderful defence. And Clare's got evidence for the continuing arms race in these signatures, because there's one signature which the hosts have got involving an olive green background with squiggles, which the cuckoo finch does not forge. And during the last 30 years, those with olive green eggs in the prinias have actually increased in the population, presumably because they're better able to spot a parasite egg. Now here's an idea for a fantastic experiment, a thought experiment if you like. What we should do is we should take some hosts with remarkable signatures like this, and we should release them on an island free from cuckoos. And then we should track their descendants over the generations, and the prediction is that these signatures would gradually fade because in a world without cuckoos, they'd no longer be needed. Well, this experiment has been done, but it started in shameful circumstances. We're going to West Africa now, where a favourite host of the Diederik cuckoo, called because its call goes Diederik, is this little weaver bird here. And this little weaver bird has got remarkable variation in its eggs, just like Clare's prinias, from pale through to blue, not spotted, heavily spotted, big spots, small spots, the whole gamut. And these little weaver birds are very good at checking out badly matching cuckoos' eggs. Now, at the peak of the slave trade back in the 1780s, some weaver birds were taken as pets across the Atlantic to the West Indies. And some of them escaped, so for the last 200 years plus, there's been a thriving population of these weaver birds on the island of Hispaniola. And it's a cruel irony that the voyage led to slavery for the African people, but freedom for these African birds, because there are no cuckoos in the West Indies. And David Larty measured the egg diversity in these cuckoo-free weaver birds and compared them with those back on West Africa, where they get clobbered by cuckoos. And you can see that the diversity in the eggs in the cuckoo-free island is much less. So that suggests there's been signature loss in the absence of cuckoos. Now, there is an alternative explanation for this, and that is known as the founder effect. What that explanation is that just by chance, perhaps on board, there was only a subset of the variation back in Africa. So there's been no change at all, there's simply a sampling problem. Well, David Larty's measurements argue against that alternative explanation, because it turns out that not only is there less diversity in signatures, but females are less consistent in the way they mark their eggs. So each female is a bit more sloppy in her signatures. There's much more variation within her clutch. And that's exactly what you'd expect from signature loss. And also there's another population introduced more recently onto another island in the Indian Ocean, and that's also lost signatures, but not so much, which is exactly what you predict from more recent colonization. So it really does look as if hosts evolve better signatures in response to cuckoos and then lose them when parasitism ceases. Well, after that little trip to Africa and out to the West Indies, let's go back to Wick and Fen. Here's a clutch of reed warblers' eggs, and the message so far is reed warblers learn what their own eggs look like the very first time they breed and then reject eggs that differ from their learnt set. And the problem they face is how fussy should they be? How should they set this threshold for rejection? Should even an egg slightly different from what they've seen before be chucked out? So let's see how good you are. Anybody vote for this as the cuckoo egg? No votes. This one. This one. This one. God, you're very good. Nobody changed their mind? Okay, here's another test. Anybody vote for this one? No, one vote. Right, this one. Yeah, few votes. This one. This one. Yeah, more votes. Anybody want to change their mind? Anybody think there isn't a cuckoo egg there? Well, there isn't. Sorry to disappoint you. And we know from DNA profiling that all those eggs belong to the reed warbler. So we have problems. Well, it turns out the reed warblers have problems too. Sometimes they reject an egg even when there's no cuckoo egg in the clutch, and we call these false alarms. Sometimes they make a mistake when there's a cuckoo egg there and accept it. That's known as a miss. And sometimes they reject an egg here, but they pick out the wrong one. And Michael Brook and Alex Koselnik and I have tried to assess the frequency of these mistakes and the consequences of those mistakes for the reed warbler's reproductive success. And that is shown in the next graph. This is actually a general problem facing everybody whenever recognition isn't perfect. Any increase in readiness to reject will inevitably lead to more false alarms. So the police face this problem in targeting criminals. Quicker arrests will catch more criminals, but at a cost of falsely accusing more innocent people. And in our own immune system, which is the task of recognizing foreign invaders, if it's too fussy, it'll target your own healthy cells and lead to autoimmune responses. So this is a general problem. Well, this is what our calculations suggest. So let's imagine there are two sorts of reed warblers. There are those very laid-back reed warblers who always accept, and there are fusspots who reject. What we're plotting here is the probability that you're parasitized from certainly having a cuckoo egg in your nest here through to not having a cuckoo egg in your nest there. And this is how well you do, how many eggs you get to raise of your own in the nest. Well, let's see how well acceptors do. Well, over here where you're parasitized by a cuckoo, you of course end up with nothing because the cuckoo egg's going to hatch and chuck everything overboard. Over here, if you're not parasitized, you do very well because you end up raising 4 eggs of your own. And this shows your payoff at different probabilities of parasitism. How well do rejectors do? Well, if you had perfect recognition and hit the cuckoo egg every time, you'd save 3. But in fact, you make recognition errors, so on average, your payoff's about 2.5. Over here, you're unnecessarily rejecting one of your own eggs some of the time, but not all the time. And our measurements show, in fact, your payoff here is between 3 and 4. And this is how well rejectors do at various levels of parasitism. And the key point is there's a particular parasitism frequency, round about 20%, above which you should do better by rejecting, and below which the mistakes just aren't worth it, you do better by accepting. Now, one possibility is that this problem could be solved by natural selection, selecting between acceptor and rejector genotypes. And in fact, on average, parasitism rates are much less than 20%, and that might explain why most reed warblers accept most of the time. But that's a very crude way of solving this problem. Surely it would be much better for reed warblers to solve this problem with their brains, simply because parasitism varies in intensity from place to place and from year to year. And in fact, our results show that indeed reed warblers do vary their rejection of model eggs with space and time. So you can have two neighbouring reed beds just a few kilometres apart, one clobbered by cuckoos where reed warblers are rejecting eggs, and another one where there are no cuckoos, where they're much less fussy. And during the last 30 years, cuckoos have declined precipitously across Britain, and the reed warblers have tracked this by dropping their defences. So not only are cuckoos looking out for reed warblers are also looking out for cuckoos. And how do they do it? Well, they seem to do it using two sources of information. First of all, they use what we call personal information. They look out for cuckoos in their own territory, and as we've shown, if they see a cuckoo at their own nest, they're much more likely to reject an egg. But cuckoos are very secretive, so this isn't a very good way of just assessing parasitism risk. Could they increase their assessment of parasitism by using social information, eavesdropping on neighbours? Well, when a cuckoo comes along, reed warblers mob it, and they make a hell of a fuss. So you listen to an alarm call and also bill snaps too. So they go on a bit, as you can see. But all this mobbing attracts neighbours. So if you watch the cuckoo being mobbed, you see all the weeds twitching all around as neighbours come along to have a look what's going on. Well, we did some experiments, Rose Thorogood, Justin Welberg and I, to see if birds learnt from this social information, and they do. Our experiments show that if you've seen a neighbour being mobbed by a neighbour's mobbing a cuckoo, you up rejection of eggs back on your own territory. So the cuckoo's secrecy is very important, not only for fooling the target for that day, but also to avoid alerting the neighbourhood. Well, not surprisingly, cuckoos have combated this with the last trick I'm going to discuss at the egg stage. Many cuckoos are grey, but some cuckoos are strikingly different, only females, in their plumage. They're bright rufous. I'm supposed to be a good cuckoo watcher, but the first time I saw one of these, I didn't know what it was. And I know other experienced biologists have been fooled too. Could coming in different guises fool the reed warblers too? Well, our experiments show that indeed it does. If the neighbourhood is alerted by a grey model adult cuckoo, they up their defences to grey, but rufous can slip through undetected. Conversely, if the neighbourhood is alerted to rufous by our models, the grey is less detected. So on average, you'd expect a balance between the two types. So coming in different guises really does seem to make it harder for reed warblers to recognise that there's a cuckoo at large. So now we can sum up the egg arms race. Hosts reject eggs and evolve signatures, and in response, the cuckoo evolves mimicry. This mimicry is so good that hosts now need evidence that there are cuckoos about to stimulate rejection. So they're alert to cuckoos, but cuckoos are very fast and secretive. Hosts now increase their source of information by eavesdropping on neighbours, but now cuckoos come in different guises to try and thwart that information. And now we come to the question which still keeps me awake at night. And the question is, why, after all this fussiness over odd eggs, do reed warblers accept cuckoo chicks? In fact, we've never ever recorded them rejecting a cuckoo chick. Now, there are 3 cues to tell this reed warbler this could not possibly be one of their own chicks. It's too big, its gape's the wrong colour, their own chicks have got yellow gapes, and there are no tongue spots. And these cues, size, colour and spotting, are exactly the cues they pick up on eggs. So why on earth aren't they picking them up on chicks too? Well, you could say poor old reed warblers can't compare their chicks, they can compare eggs, but not chicks, because the cuckoo hatches out first and chucks the eggs overboard. But even in the few cases where cuckoos hatch after some host chicks, so you can compare, there's still no rejection. Perhaps the cuckoo chick's especially charming. No, that's not the answer, because reed warblers will accept robin chicks or dunnock chicks. In fact, they don't show any fussiness about odd chicks. Maybe it's harder to recognise an odd chick, because chicks change daily as they grow, whereas eggs always remain the same. Well, maybe. And of course, maybe you save more by rejecting early, because then you could save all 3 eggs, whereas over here, at least after the cuckoo chicks ejected your eggs, you've lost everything. So perhaps you should put your defences early on rather than later. And people have done mathematical models to show actually chick rejection's unlikely. But beautiful theory can always be trumped by natural history, and there's some recent observations of an Australian warbler called the Gerygone rejecting odd chicks, and quite often rejecting cuckoo chicks. Just look at this wonderful clip. Now the first one, the nest waves about a bit, but the second one, you'll be able to see much better what's going on. This Gerygone is getting a cuckoo chick. It's still alive, and it's going to chuck it out. And the cuckoo chick is on the lip of the nest now. It's still writhing, and the warbler's going to grab it and get rid of it. Here's another clip, easier to see. There's a cuckoo chick, give it a good shake, and get rid of it. So these hosts have taken the arms race to the next stage, and they're rejecting odd chicks. And what's beautiful is that the cuckoos have replied with chick mimicry. This is some work by Naomi Langmore and Rebecca Kilner. This cuckoo parasitizes hosts with black skin. This cuckoo parasitizes hosts with yellow skin. This cuckoo parasitizes hosts with pink skin. In each case is a beautiful match. This is an older arms race in Australia, so maybe there's simply been more time for defence and trickery to escalate to the chick stage. Well, let's go back to Wick and Fen for one last look at the reed warblers. Cuckoos don't have to match reed warbler chicks in colour or begging calls, because the reed warblers will accept any chick, but the cuckoo does have one final problem. The cuckoo chick needs as much food as a whole brood of 4 reed warbler chicks. How on earth does it stimulate these little warblers to bring enough food? Well, first of all, we thought that maybe it's just simply the large size of the cuckoo that's stimulating. Blackbird chicks are about the same size as cuckoos, so we gave reed warblers a single blackbird chick to see how much they'd feed it. They would accept the blackbird chick and they would feed it, but they brought it less food than they would to a cuckoo of the same mass. So just being big isn't enough stimulus for the cuckoo. And then we realised that the warblers listened to their chicks as well as looking at them. And this little clip, narrated by David Attenborough, just focus on the amazing begging call of the cuckoo chick.
Having cleared the nest of all competition, there's now just one hungry mouth, devouring all the food the warblers can bring to the nest.
Now that begging call is absolutely extraordinary. It sounded to us not like a single chick, but a whole brood of hungry chicks. So we wondered if it was the sound that was the key trick. So now we repeated the experiment with a single blackbird chick in the nest, but now it was given a helping hand or helping sound in the form of a little loudspeaker. And every time the blackbird chick begged, we broadcast cuckoo begging calls through the speaker. And it's very important to know that these begging calls didn't alter the behaviour of the blackbird chick, but they did alter the behaviour of the reed warbler parents. Compared to controls, this plots the number of loads brought, when we broadcast cuckoo begging calls through the speaker, the reed warblers upped their rate. They nearly doubled it. And in fact, they brought as much food now to the blackbird as they would to a cuckoo of the same mass. And broadcast of a brood's begging calls had the same effect. So the nice simple story so far seems to be the cuckoo female gets its egg accepted by visual mimicry, whereas the cuckoo chick gets enough food by vocal mimicry of a brood of host young. Now, a good recipe for science is seek simplicity but distrust it. And it was Becky Kilner who realised that this explanation is too simple. At a week of age, cuckoo chicks do indeed sound like a brood of reed warblers. But as the cuckoo chick grows, it boosts its calling rate more and more, so by 2 weeks, it sounds like 2 broods of reed warblers, but it still gets the same amount of food as 1 brood. So we realised we had to go back and understand what cues reed warblers picked up from their own young to determine how much food they should bring. So we varied the number of chicks in the nest from just a few to double the normal brood size, 8. And we also added to the begging chicks a lot of begging calls or just a few extra begging calls. And our results showed that how hard the parents work varies with what they see and what they hear. The visual cue is best described by the begging gape area on show. And that's a good visual cue because obviously more gapes more gape area, and older chicks with bigger gapes, more gape area. So that gives you a rough idea of how much food to bring. More broods, bigger broods need more food, and older chicks need more food. But the vocal cue begging also adds on to the visual cue. More hungry chicks beg more rapidly, and so this enables the parents to fine-tune their provisioning in relation to brood hunger. So the cuckoo needs to somehow plug in to this provisioning scheme. And you can see the cuckoo's problem here. This is what the provisioning scheme is designed to raise for reed warbler chicks. Here's the cuckoo chick. Now it's bigger than any one reed warbler chick, but it's only got one gape, and that gape area is very poor compared to the gape area which reed warblers expect to see. And in fact, this mismatch becomes bigger and bigger the older the cuckoo gets. And that's why the cuckoo has to boost its vocal cue more and more to make up for this poorer visual stimulus. So what the cuckoo has done is it's tuned in to that provisioning rule, that provisioning equation, and the result is it gets as much food as a whole brood of reed warblers. There's another cuckoo in Japan which has got an equivalent trick, but it's a visual one. This is a little robin feeding a Horsfield's hawk cuckoo, which doesn't have such an elaborate begging call, but it's got a little bare patch of skin on the wing here, whose colour matches the gape of the cuckoo. And whenever the robins come back with food, it waves the gape about, and indeed sometimes the robins will offer food to this patch. And if you blacken the patch, the robins then bring less food. So this little cuckoo has got a visual trick of simulating more gapes rather than simulating more chicks through a vocal trick. Now you might think, well, we would never fall for anything like this, but oh yes, we are every day. Here's my favourite example, an experiment done by Melissa Bateson in a psychology department in Newcastle, where people were asked honestly to pay for their coffee every morning. And on alternate weeks, next to this notice asking people to pay were either some flowers or some eyes. And if you track how much people paid for their coffee, you'll see that they paid more when the eyes were on show rather than flowers. And in fact, this one here was particularly effective. This one, not quite so good. What's amazing is at the end of this experiment, Melissa debriefed everybody and said, well, why did you pay more for your coffee when eyes were on show? And they all said, well, we didn't notice the eyes. So this stimulus is acting unconsciously on the participants in the same way, presumably, that these simple stimuli are manipulating hosts. So cuckoo host arms races provide a window, perhaps, onto our own vulnerability too. I want to end with this very final slide on an elegiac note, if I may. This beautiful photograph of a cuckoo flying over the fen was taken by Richard Nicol last summer. Cuckoos have declined across the UK by 65% in the last 30 years. It's a symbol of our diminishing natural world, in which 1 in 5 bird species across the globe are now threatened by extinction, mainly because of us. How sad it would be to lose this amazing bird. We'd lose not only our harbinger of spring, but a corner of Darwin's entangle bank, I think, with some of the most amazing natural history that you can see anywhere on Earth. Thank you very much. Thank you very much.
Questions? Yes, can you see that? They'll bring a microphone to you.
Yeah.
Thank you. You said that where it was the first time that a reed warbler had bred, you suspected that it imprinted upon the first egg that it saw. Did you do any experiments for the following season to see whether reed warblers which might have imprinted upon a cuckoo egg in their first season were still imprinted on it in the following season?
No, that's not been done between seasons, but it's been done within a season. When birds lay replacement clutches. But that's a very good question. No, that's not been done.
Thank you very much.
Yes.
Right at the back.
Hi. I'm always intrigued by the similarity with sparrowhawks.
Yes.
So beyond what you mentioned, is there any other explanation for that?
So cuckoos do look rather like hawks. As you can see here, they've got underpart barring with long tails and long wings. And in fact, in the old days, the ancient Greeks thought that the explanation for cuckoos disappearing in the autumn was that they changed into hawks. Aristotle doubted this because cuckoos don't have talons or a hooked beak. But even now, people mistake cuckoos for hawks. And we think this might explain why on Wick and Fen, that grey morph of females is more common than the rufous one. Namely, the grey morph of female has an extra advantage of being rather hawk-like and dissuading host attack. And our experiments suggest that. But in other parts of Europe, actually, the rufous morph is the more common, and we don't know why.
Is there any advantage to the host species, the host bird? Is there any advantage to them from being parasitized by a cuckoo?
Okay, so the question is, from John, is could the host ever get any advantage from being parasitized by a cuckoo? And I think the answer is, in cases where the cuckoo chick chucks everything overboard, no, you lose everything. It has been suggested that where cuckoos are raised alongside host young, you might get some advantage. And the advantage you might get is by avoiding punishment by the cuckoos, the adult female cuckoos, who might come back and punish any host that dares reject. And this is a subtle argument, but it could work. It could be you accept the cuckoo chick alongside your own chicks through fear of punishment, because if you're punished and reject the cuckoo chick, you lose everything. But on the other hand, if you agree to accept the cuckoo chick, at least you get to raise some of your own young. So in theory, where cuckoos are raised alongside host young, the cuckoos could act like the mafia and force hosts to accept. But in our system, this isn't going to work. You lose everything. You should get rid of that cuckoo egg. And we've got no evidence that cuckoos ever come back and check.
Yes. Down here, well, why don't you take the one at the back first? A second. Yeah.
Thanks. I'm thinking like a male here. And as of course you know, there's a huge amount of false parenthood in various birds. Now the male's interest in this system is different from the female's interest, obviously. Does the female force the male to be monogamous in some way?
Okay.
Is that mimicry part of it, or do the males cheat?
So you've raised a very good question, and that is how the mimicry is controlled genetically. And the answer is that in cuckoos we don't know. So we have some genetic evidence that it's only female races that are distinct, with males cross-mating between the female races, and so maintaining the cuckoo as the one species. Now, those nice different mimetic lines will then only work if females have got control of the egg mimicry. And that could work in birds because females have got a distinct sex chromosome, the W chromosome. And if that controlled egg colour, that might explain that. There are other parts of Europe where people have suggested from genetic analysis that the males are in distinct strains too. So they're faithful to the host that raised them, just as females are too. So there the cuckoos seem to be behaving a bit more like separate species. And it could be we have a glorious mix-up at the moment because humans are destroying habitat and breaking it up into little patches where the mimicry might be breaking down because males are more often mating across the strains. But the bottom line is we don't yet know.
Yes, there's one there.
So is there any difference in whether the male or the female throws out the cuckoo's egg? Is there a difference in discrimination by the male or female?
That's a great question. So Arnon Lottem did his experiments with great reed warblers where only the females incubate and only the females reject eggs. And he chose great reed warblers because it's nice and simple. In our reed warblers, actually both sexes share incubation and both male and female will reject eggs. And that raises a very interesting learning problem. Female reed warblers will have the same eggs more or less throughout their life, so presumably they could learn early on, and that would form a template for the rest of their life. But if a male cuckoo swapped mates, he'd have to learn anew what his mate did. And I think that's the prediction, but we've not yet tested that, and it'd be very interesting to do so.
Yes, at the front side there. While the thing's coming, what dictates the pattern on the egg?
So genetically, that's also not known. It's not even known physiologically how that's made. So you might imagine squiggles are made if the egg twists in the oviduct.
Yes.
But that's not known.
Okay. So
Actually, it's a question that overlaps with John's.
sorry.
Yeah.
how does that evolve? I mean, how do they paint their eggs, or is it just completely chance, the patterns that come out at the time when the egg is going down the oviduct and having the shell put on?
So I don't know the answer. This is exactly what Clare is now doing with her cuckoo finches in Africa. We don't know. I mean, it's known in chickens, for example, that egg patterns are inherited, and it's known in weaver birds. And actually, in those village weaver birds, experiments have been done showing that there's autosomal control of egg colours and patterning, so both male and female influence egg patterns. But we don't know. It's a fascinating question.
Yes.
It's a bit of a strange one, but why do they chuckle when they lay an egg? What's the benefit?
Why do they chuckle? I don't know. You'd think that that would be a giveaway sign to reed warblers. We've not done playback experiments to see if they cue into that. I think the chuckling might be a keep-out signal to other female cuckoos, that this is my territory and I'm working here and nests are being parasitized. This is an unprofitable place for you to come to. But the function is not known. It's a good question.
That one there. Okay.
Well, what information have we gotten out of any new information about how genetics works in the natural world?
Well, that's quite a big question. So in the cuckoo, I'm afraid we don't know. So as you've gathered, my passion is bird watching, and I've really focused on behavioural experiments, and we don't yet know. But there's some breeding experiments going on now with cuckoo finches where we hope to solve that problem.
Yours?
I'd be interested to hear from a phylogenetic sense, why is it so rare when in other lineages it's not that rare in terms of brood parasitism?
What's the question? Why within the cuckoo lineage has it cropped up 3 times?
In birds compared to fish or insects, for example.
Yes. I don't know. It's a puzzle why parasitism isn't more frequent. So actually, the brood parasitism does occur, but it occurs within species cheating on their own kind. So in Britain, a famous example is moorhens, which will have their own clutch of eggs, but then try and foist a few extra eggs on neighbours to get some extra eggs into the system. So this part-time cheating seems to occur quite commonly across birds. It's the full-time cheating which is rare. And one possibility is maybe cheats get caught in the end. And I think one of the main results we've got is actually being a cuckoo is very hard work because the hosts fight back.
This sort of follows on from a previous answer. You mentioned that female cuckoos will sort of cultivate a group of nests, host nests. How territorial are female cuckoos against other females?
Okay, so they are territorial. Usually a female will have a patch of hosts to herself, but where density of cuckoos builds up in an area, sometimes you get subordinate females laying. And in some of the nests Mike and I studied early on, where cuckoo parasitism levels were higher, we found 2 cuckoo eggs in the same nest. So a female will only ever lay 1 egg, but sometimes a second female will come along and lay. And if both cuckoo eggs hatch out, then there's the most enormous battle between the cuckoo chicks, and one eventually will win, usually the early hatching one. So that's why a second cuckoo should be looking out for the first cuckoo's egg, and we're really puzzled that they don't do that. But in Australia, there's some evidence that female cuckoos do indeed remove prior cuckoo eggs. So again, it looks as if the arms race has gone on a stage, not only for the cuckoos, but also for the hosts too.
Yeah. Have you got one at the back there? And then the last one in that part there.
It's a really fascinating talk.
Thank you.
My question is, why cuckoos, at least the European ones, choose host birds that are so much smaller than themselves?
Yes.
You know, why not go for a blackbird or something a little bit closer?
Yes. So they probably go for smaller hosts because in general small birds are more common than big birds. Actually, experiments have shown that blackbirds and song thrushes, which would be 2 hosts I imagine you're perhaps thinking of, are not suitable as hosts for various reasons. One is that the cuckoo chick can't eject song thrush chicks out of the steep and slippy nest, which is mud-lined. And the other is that blackbirds won't accept a cuckoo chick, and we don't know why. It's very interesting, that. But we also think there are some hosts that have actually beaten the cuckoo. So rebuntings and chaffinches, for example, you might think, well, why don't cuckoos go for those? Well, it turns out they've got wonderful signatures on their eggs. And Mike and I have actually failed to fool either rebuntings or chaffinches with the model egg, however perfectly we paint them. They're even sharper-eyed than reed warblers and medipipits. And if we're right, the discrimination evolves only in response to cuckoo parasitism. The suggestion is that these might be old hosts that perhaps won the arms race. But why they've not lost their signatures, like those birds in the West Indies, we don't know. So that's another puzzle.
Okay.
Is there any evidence that birds may opportunistically lay their eggs in the nests of the same or similar species, opportunistically, if you understand me, simply because it's a convenient thing to do? And if so, could this have been the way in which the cuckoo behaviour evolved? Because I'm fascinated to know how the cuckoo parasitic behaviour would have evolved in the first place.
Yes.
Do you understand what I'm driving at?
They're very good questions. So in the honey guides, it could have evolved because they breed in, they parasitise bee eaters, and quite often whole nests are in short supply. So if there's competition for whole nests, it could be, and you can't get a nest for yourself, it could be that you take over somebody else's nest, and then that's a route to, instead of taking over the nest, just lay in it and leave. For the cuckoos, we think perhaps their habit of feeding on hairy caterpillars might be the starting point, because the parental cuckoos also feed on these gluts of hairy caterpillars. And when food is very, very abundant, there's a potential to lay lots and lots of eggs. So maybe this temptation then leads to laying eggs in other birds' nests, and that could then give rise perhaps to full-time parasitism.
Well, one last one here at the front. There's a thing coming.
Yeah.
I'm thinking about the Pacific parrotlets that were naming their chicks, and by doing that, they were actually singing a song to them before they were hatched, and so they could. They knew each other's family name,
yes.
And then when the chicks were hatched, then they had their individual
yes.
names.
Yes.
Do passerines or do
yes.
their hosts of the cuckoos do this with their own chicks, or might they potentially
yes.
develop
yes.
this?
So there is some evidence from a recent study in Australia that superb fairy wrens will sing to their chicks while they're unhatched and still in the egg. And the chicks then pick up this signature, if you like, and incorporate it into their begging call, so the parents know that that must be one of their chicks. And they suggest that this is why superb fairy wrens can sometimes reject cuckoo chicks. But the puzzle there is, why don't the cuckoo chicks eavesdrop on this little signature? They should be listening too. And I don't know the answer to that. My guess is whenever hosts come up with a trick, the cuckoos will be there to infiltrate.
It's obvious, Nick, you could continue talking about this fascinating biology all night, and thank you for a wonderful lecture. It's my great pleasure now to give you the Croonian Lecture Awards themselves.
Thank you very much.
Thank you.
Thank you. That's
well done. Fantastic. Good question.